Hi everyone, so today we are starting on our second last chapter on arenes. Okay, so what are arenes? Actually, I think most of you would have heard of it. They are actually called benzene ring also. They are known as the aromatic hydrocarbons. Okay, aromatic because last time when they first discovered benzene, right, they have a aroma, a kind of a good smell. But now we know that benzene itself is actually carcinogenic, so I won't advise you all go and sniff it. Okay, so what is the structure of benzene ring like, right? It is planar structure, as you can see here. It has a hexagon shape, all right, with a ring of electron above and below it, all right, as shown here. Okay, each carbon, right, is sp2 hybridized. I think you guys would have known what is hybridization, okay, after the intro to organic chem, right? Okay, so each sp2 hybridized C atom forms 2 sigma bond, right, with 2 other carbon and 1 sigma bond with a hydrogen. So it means that each of the C is bonded to 2 other C and bonded to a H. Okay, and the unhybridized 2p orbital, right, actually overlaps with each other, all right, across all the neighboring C atoms, so that the electrons, right, the electrons are free to move around all 6 p orbitals, all right, so forming a sort of like a cloud above the carbon atom, all right. So this is what we call a delocalized pi electron cloud, and it is this delocalization, right, that actually gives benzene the extra stability, all right. So sometimes we call it benzene ring is resonance stabilized, all right. So let's look at the, oh yeah, so please take note that the bond length, right, the CC bond length is the same for all 6 bonds, all right, 1, 2, 3, 4, 5, 6. They have all the same length, all right, and the bond angle is 120. Okay, so proof of the delocalization, right, of this resonance structure. So what scientists actually did, right, was that they actually hydrogenate, right, 1 double bond, CC double bond, and they realized that it gives out 120 kilojoules per mole. All right, so logically you would expect that if we hydrogenate 3 double bond, CC double bond, you will get like times 3, right? Okay, so you expect it to give out 360, but in actual fact, right, in real life, when we hydrogenate your benzene ring, right, it only gives out 209. So where did that 151 kilojoules per mole goes to? All right, so this is what we call the resonance energy. So when they actually delocalize the electron, right, this 151 was actually given out, all right, as a kind of like stabilization energy. So the overall enthalpy, right, actually dropped, all right, from this here to here. All right, so how do we actually explain this? Why does it lead to stabilization, right, when we have resonance? Is because when we spread out the pi electron, right, because you know electrons are negatively charged. Okay, when we spread them out over a greater area, okay, it leads to charge dispersion. All right, so charge dispersion leads to stability. All right, in organic chem, this concept is always holds true. Charge dispersion leads to stability. Okay, so now when we look at reactions of benzene, right? Benzene itself is electron rich, so you attract electrophile, like electron loving. Okay, but it undergoes substitution rather than addition, even though it is unsaturated. Because, right, if you do the addition, right, you will destroy this aromatic system, which actually, if you remember, stabilize the structure, right? So if you break up the double bonds, right, then this stabilizing system will be gone, right? And the molecule doesn't want that. Okay, so we learned in alkenes, right, that we only need a partially charged electrophile for reaction. But benzene ring, right, you will learn it needs a fully positively charged electrophile, not just a partially charged electrophile. All right, why is that so? Because when we delocalize the pi electron, right, it makes the pi electron less susceptible. It means less concentrated, not localized in between the two carbon atoms. So when this happens, right, it actually makes the CC bond less electron rich compared to the CC double bond in alkene. All right, so you can just think of it like the double bond is not localized between two atoms. All right, so it is actually a little bit more dispersed in terms of electron density. Okay, so a general equation is what happens here. All right, we'll go into detail for this soon. Okay, for now, let's look at all the electrophilic substitution reaction of benzene ring. Okay, so the first reaction is when it reacts with a halogen. With a catalyst, you will actually substitute one hydrogen for a halogen. All right, and if you're reacting with a RX, right, halogenal alkane, you actually need a Lewis acid to create the electrophile, and then you will then plant the R group on the benzene ring itself directly. Okay. The third reaction that benzene ring will undergo, right, is actually nitration, where you will get the two concentrated acid, right? All right, two concentrated acid with heat, all right, to get the nitro group onto the benzene ring itself. Okay, nitrobenzene itself is yellow. Okay, if you want like di or tri substitution, all you need to do is to up the temperature, all right, increase the temperature. Okay, so that more substitution may take place. Okay, nitro group itself is deactivating. So you got to bear in mind that after you put in the first nitro group, right, you need even more energy to get the second one in. All right, so now we look at the reactions in detail. So when we want to stick a halogen on the ring directly, we will need to use a Lewis catalyst, Lewis acid, right? Lewis acid catalyst, all right? This allows us to produce our Cl+. All right, so this is a fully charged electrophile, so that it can actually directly attach itself to the ring. Okay, this is not free radical sub, so please take note of that. There's no need for UV light. Okay, for mechanism-wise, right, the first step is to generate the electrophile. So you can see that the chlorine, right, what happens is that the bonding pair of electron goes onto one chlorine, and that Cl minus goes onto your Lewis acid, all right? And that leaves you with your electrophile, which is Cl+. Okay, step 2, which is the rate determining step. The benzene ring, right, one pair of electrons will actually come out to attack the electrophile and forming the new covalent bond, all right, which is this bond highlighted here. Okay, then you notice that the positive charge is delocalized over 5 carbon atom. All right, positive charge delocalized over 5 carbon atom. And this atom here, right, where the substitution took place is sp3 carbon. So it means that it has a tetrahedral shape. Okay, so that is something that we need to take note of. So after the substitution, right, how do we restore the aromatic structure is by taking both of the bonding electrons between C and H and returning it to the ring. Okay, so that in a nutshell is your mechanism. Next, we look at Friedel-Crafts alkylation. It's pretty much the same thing, except that instead of a halogen gas, right, you now use a halogenal alkane. All right, so it means that your electrophile is actually your R group. All right, your R group becomes your electrophile. Okay, so you form this new CC bond. All right, and then you return the lone pair of electrons back to the ring. Okay, Friedel-Crafts alkylation is not really in H2 syllabus, but I think good to know just for information, right? It works in exactly the same way as your normal Friedel-Crafts alkylation, except that the C now has a C double bond O. All right, so whatever you want to suck onto the ring, right? Just make sure that the C that is going to be connected to the ring is first connected to a halogen. All right, so that when you get rid of the halogen using a catalyst, you will create a carbocation here. All right, and that carbon will be the carbon that is attacked by the lone pair of electrons from the ring. Okay, so now we look at nitration, right? This is a rare kind of reaction where you have two concentrated acid being added together. All right, so what is the purpose of having those two concentrated acid? We actually mix them together to generate the electrophile. All right, so sulfuric acid protonates the nitric acid, and then the nitric acid kicks out the water and forms the electrophile. All right, so the rest of the reaction is pretty much quite similar to your earlier electrophilic sub, so we won't go into more detail. Combustion is as per normal for normal hydrocarbon. Okay, reduction, you can reduce the hydrogen, right, using nickel at high temperature, high pressure, but this is a pretty drastic condition. So normally we say that benzene ring normally isn't like reducible. All right. All right, now we move on to talk about activating and deactivating substituent. Okay, so a major part of benzene ring chemistry, right, A ring chemistry, is about finding out what will a substituent do to the rate of reaction and the position of subsequent substitution on the ring, right, once it's on the ring itself. All right, so there are two kinds of substituent. One is a electron donating kind, which will increase the pi electron density because they donate electron, right, towards the ring. Okay, the electron withdrawing one will actually decrease the electron density, and hence the reaction rate will drop. All right, so there's actually two ways electron can be donated or withdrawn from the ring itself. So number one, it flows through the sigma bond, which is what we call a inductive effect. All right, and the other kind is flowing through the pi bond, which is what we call the resonance effect. Okay, inductive effect, right, is only possible when there's a difference in electronegativity. All right, alkyl group will donate electrons inductively, right? Because of the configuration itself. So it points away from the alkyl group. Okay, so can we have both effect at the same time? Yes. In fact, two very common substituents, your amine and your hydroxy group, right, are both have both inductive and resonance effect. All right, so for us, right, H2 syllabus, we just need to know whether overall is it electron withdrawing or electron donating. Okay, so from the data booklet, right, you realize that the activating group are basically normally saturated. All right, the first atom that's bonded to the ring is actually saturated. Okay, they're normally activating, and they will direct the next substituent to position 2 or 4. All right, but for those that are unsaturated, right, normally they will deactivate the ring and will only direct the next substituent to position 3. Okay, so there's this anomaly group, right in the middle. This is like a sore thumb, right? They are saturated group, but yet they are deactivating, and they direct to position 2 and 4. So it's a bit strange, right? They are deactivating and yet they direct to position 2 and 4. Okay, so halogens, please remember, right? Okay, so this is like a quick check for the first part of the lecture. So for example, if you have chlorine with a catalyst, you simply note that the R group will direct to the 2nd and 4th position. All right. For halogens, right, because they are deactivating, so you need to heat the mixture to make sure that the reaction goes. But it is still 2,4 directing. All right, still 2,4 directing. Okay, lastly, the Friedel-Crafts Alkylation. So, no, depending on where you want to link to your R group, right, you just put in place a halogen first. All right, and then that will be where you form the new covalent bond. Okay, so the last question, this substituent is, excuse me, this substituent is actually deactivating. Excuse me. So you actually need a very high temperature to make the reaction work, and it is going to be 3 directing. Okay, so next we're going to look at alkyl benzene. So this is the overall reaction map. We're going to look at each one in detail now. So nitration is pretty much the same thing, except that because the alkyl group, right, is activating, so we need a a milder temperature. So 30 degrees will allow us to do the substitution. Okay, if we increase the temperature to 100 degrees, right, you can actually score a tri-substitution. So the mechanism is pretty much the same, except that you will need to take note that this positive charge, right, is delocalized and opens up towards the place where there's substitution. All right. Other than that, everything else is pretty much the same. Okay, same thing with the halogenation. Okay, for free radical substitution, right, or metylbenzene, the conditions are pretty much the same as your alkanes, if you remember them. All right. For oxidation, right, this is a new reaction because for an alkyl group, right, normally if you put it through hot acidified chemical, nothing will happen to it. But if it is a side chain on the benzene ring, and on the first C, right, if there is a H on the first C, you will cause it to be oxidized to carboxylic acid. All right. Okay, so this is one example that you can see. This is a chemical test to distinguish between benzene ring and any alkyl benzene. All right, so please take note that you require at least one hydrogen attached to the carbon directly bonded to the ring. All right. Just for your information, if the R group has 2 carbon, right, the extra carbon that was cleaved off will form carbon dioxide. And if the R group has 3 carbons, the 2 extra carbon will form ethanoic acid. Okay. The Friedel-Crafts alkylation is pretty much the same. Desalation, the same. Okay, so this quick check, just to show you how the oxidation works for the side chain on the ring. So if you have 2 carbon, so you will get your carbon dioxide. All right. So that's it for the lecture part. It's pretty short. Let's go ahead and look at the MCQ part. All right, let's carry on with our practice, our MCQ practice. So we have question 1. Which type of reaction do step 1 and step 2 illustrate? All right, so step 1, you actually have electrophilic substitution. Step 2, you actually have a nucleophilic substitution. All right. Okay, so basically, how do we know that step 1 is a electrophilic substitution? Okay, so we basically look at the functional group that it reacts with. Okay, so likewise here, right, this is something like a RX, halogenal alkane. All right, and then the ammonia gas actually goes into a tag. All right, so it is acting as a nucleophile here. All right, so this Cl is a delta plus, which is acting as a electrophile. Okay, my apologies. The Cl is delta minus. So the S should be the one that's delta plus. Okay, so the electrophile is actually your SO3H. Okay, question 2. Which of the following synthetic groups is correct? 1 and 3 are fine. 2 is not correct. 2 is not correct because of this last step. All right, you cannot actually nitrate using dilute HNO3. All right, it's not strong enough. Okay. Question 3. Which of the following sequence of steps is expected to give the best yield for the synthesis of 3-bromo-4-methyl-phenylamine? Okay, so what do you want to do? You want to form a benzene ring, right? So you want 3-bromo-4-methyl-phenylamine. Okay, so first of all, you actually get a alkyl group in. Then after that, you introduce in your nitro group on the 4th position. All right, then you brominate it, and then after that you reduce the NO2 to NH2. Okay, so question 4, which of the following is a possible identity of 1? A 1 would be, okay, so if you put option D as 1, right, what will happen in the first step is you will oxidize this to carboxylic acid. Then after that, you will substitute the OH with a Cl here. And then after adding an ethanol, you will actually form the target molecule. All right, so D is correct. Which is the product formed when benzene reacts with iodine chloride? Okay, so iodine chloride, your electrophile is actually the iodine. Okay. That's why iodine goes in. Due to electronegativity, in case you have forgotten. Okay, last question. Which row gives the synthetic route that will lead to the highest yield of the product? Right, so step 1 says that you actually do a nitration. So that will give you a NO2 here. And then followed by a bromination. We'll add in a Br here. And then the last step is to oxidize this to a carboxylic acid. Okay, so all the step 1, 2, 3, right, actually follows our directing effects to give them the major product as the yield. All right, so that's all we have for you this week. Pretty short lesson on arenes.